My name is Manasi Vartak, and I am a graduate student in the MIT database group. Today, I'm going to be talking to you about a new benchmark that we're developing for genomics. And this thing is a joint collaboration between the MIT database group and Intel. So right now, we've heard about R, we've heard about Hadoop, XLDB, and so on. So we can finally see which one is actually useful for genomics. So why do we need a genomics benchmark? If you go through the list of talks for this conference, you can see that genomics and basically medical applications are becoming really important. They're becoming a major source of what everyone calls big data. And it's particularly true for genomics because for $100, you can now genotype millions of your SNPs, and you can probably sequence your genome for less than $1,000. And that's generating about 6 terabytes of data per facility per day, and that's just going to keep growing. So we have a lot of data. We don't know how to scale our algorithms. If you look at the previous benchmarks in the database community, a lot of them only focus on database operations, selects, projects, joins, and so on. Or there are simple aggregates. Is it averages, min, max, and so on, which is not really sufficient for genomics and other related scientific applications. What genomics needs, as you've probably guessed, is we need linear algebra. We want to do, by clustering, we want to do regression. We also want to do a lot of statistics to see if our results actually make sense at a large scale. And of course, we need database operations. So our benchmark is called GenBase. We're working with microarray data, which just tells you how much of a gene is expressed under various circumstances. We also look at gene and patient metadata. Basically, you can think of everything as dense floating point matrices and regular database tables. We work with 5 queries, which are a combination of database operations, like some joins, selects, and so on. And we have 5 analytic components: regression, covariance, biclustering, SVD, and statistics. These have been identified by talking to bioinformatics folks at the Broad Institute and Novartis. This is by no means an exhaustive list of genomics operations, but we think that this is a good representative sample. So this is what a query looks like. You begin with the data, select, say, patients between a certain age range who have lung cancer. Then you build a regression model, and then you use that model to predict disease outcome for new patients. And once we have these 5 queries, we run them on a variety of systems. These include R, Postgres, Hadoop, XLDB with some hardware acceleration, and a popular columnar DBMS that you can guess. We also try this on data of different sizes and run it on single and multi-node configurations. Here are some very preliminary results. These are single node. If your data set is small enough to fit in memory, R is pretty good. But the caveat is that you cannot have data management operations. The minute you have selects and joins, R is not going to be a good option. But what you can do is store the data in a DBMS, pull it out, and then use R for doing analytics. Madlib, which is an in-database analytics library, and Hadoop turn out to be extremely inefficient. So Hadoop is great for batch processing, does not seem like it's a good thing for linear algebra or statistics. Interestingly, as the data scales up, XLDB surpasses the rest because it can do linear algebra, statistics, and data management. Several of our systems time out because we have a timeout of about 3 hours, and they don't finish. Once the data size becomes large enough, R is going to run out of memory. We could possibly use the distributed R system from HP, and it would be worth giving that a shot. So this is what the results look like. We are next going to be running it on our largest data set, running all our code multi-node, and hopefully have a paper later in the fall. So please come talk to me at the poster session. Thank you.